Hello everyone, I'm Jessica Rigley and I'm a PhD student at Cambridge, and today I'm going to talk about an analytical model which I've developed which can predict the levels of dust which are dragged into the habitable zone of a star from an outer planetesimal belt. So as you likely know, debris disks are the remnants left over after the dispersal of a protoplanetary disk with a belt of planetesimals undergoing collisions to produce dust grains. And these dust grains can be influenced by many things, including the star's radiation pressure, as well as Poynting-Robertson drag, which causes dust to migrate inwards. And we usually detect this dust from its thermal emission in the SED of a star. So as an example, this is Eta Corvi, and you can see that there's a far infrared excess, which implies the presence of very cold dust. However, many stars also show mid-infrared excesses, implying the presence of dust much closer to the star. So this warm habitable zone dust is known as exo-Zodiacal dust, in an analogy to the zodiacal cloud. And this can tell us about the architecture of the inner regions of planetary systems, as well as being a source of noise and confusion for directly imaging Earth-like planets. So this shows the fraction of stars which have a given mid-infrared excess. So the zodiacal cloud has an excess of around 0.01%. And previously with WISE, we could detect that around 1 in 300 stars has an excess of at least 10%. More recently, we can detect down to 0.1% using nulling interferometry. And the limit for confusion for directly imaging Earth-like planets is around 10 times the zodiacal cloud. So there are various mechanisms for how this dust could get there. In young systems, it could be that there's an in situ asteroid belt. However, these rapidly grind down by collisions. In other systems, it could be a transient phenomenon, for example, dynamical instabilities, or a recent giant collision similar to the moon-forming impact. In other systems, it could be that comets are scattered into the habitable zone to deposit dust. And another possibility is that dust is dragged into the habitable zone all the way from an outer planetesimal belt. So the Large Binocular Telescope Interferometer uses nulling interferometry to cancel out the stellar emission, allowing it to resolve dust very close to the star. So recently the HOST survey was conducted to search for exozodiacal dust around 38 nearby main sequence stars, and they found a detection rate of 26%. However, only considering stars with known debris disks, they found a detection rate of 78%. So what does this tell us? So this implies that there's a correlation between the presence of a cold planetesimal belt and warm exozodi. And for that reason, I'm going to focus on Poynting-Robertson drag from an outer belt as a potential source of exozodiacal dust. So to model this, we wanted to find a two-dimensional distribution of dust grains in a debris disk as a function of both radius from the star and grain size. So previously there had been simpler analytical models. So in 2005, Wyatt found the radial profile of grains in a debris disk, only considering a single grain size. And they showed that the radial profile depends on a ratio of 2 timescales. So when the Poynting-Robertson drag timescale is very short, grains migrate in towards the star without colliding. However, when the collision timescale is very short, instead grains are depleted just inside the planetesimal belt, and very little dust reaches the inner regions. However, we don't just have a single grain size, we have a whole distribution of grains. So in 2011, Wyatt et al. Modeled the size distribution within a planetesimal belt, including the effects of collisions and PR drag. And they found the standard result that for a collisional cascade, the differential size distribution of dust has a slope of -3.5. However, they also found that below a critical particle size, you get a turnover in the slope of the size distribution. And this is determined by the grain size for which the timescales for PR drag and collisions are equal. So for the small grains, they're dominated by PR drag instead of collisions. So for our two-dimensional model, we combined the two previous models together. So this shows the contributions to the optical depth for different grain sizes at different radii from the star. So we start off with a planetesimal belt at some radius from the star, and we give it a size distribution using the 2011 model, considering grains from the blowout size all the way up to centimeter size grains. And then we assume that each grain size evolves independently inwards of the belt. And for each grain size, we use the 2005 model to find its radial profile. And you can see here that for the large grains, they're depleted very rapidly inwards of the belt. And this is due to them being more susceptible to collisions, whereas the small grains migrate inwards with very few collisions. And so they have a much flatter radial profile. Our model is validated against a numerical model from Van Lieshout et al., who self-consistently model collisions, PR drag, and sublimation. And as you can see here, overall, we reproduce the main features of the distribution. But the advantage of our analytical model is that we can rapidly explore the parameter space. So here I've shown the fractional excess at 11, 24, and 70 micron for different masses of the outer planetesimal belt and different radii of the belt from the star. So as you can see, we get the brightest excesses for belts which are very close to the star and have very high masses. And I've also shown here some detection limits. So I've shown 10% for photometry, so something like Spitzer and Herschel. And then at 11 micron, I've shown 10% for WISE. And I've also shown 1% and 0.05%. And these are limits from something like nulling interferometry. So for example, Keck and LBTI. So if we compare these detection thresholds, so here I've shown with the dashed lines the detection thresholds for 24 and 70 micron, and then the solid line is the detection limit for LBTI. And as you can see here, we predict that if a planetesimal belt can be detected at the longer wavelengths, it can also be detected by LBTI. So what this is telling us is if we've detected a debris disk, we should also see detectable levels of exozodiacal dust. So if we don't detect exozodiacal dust around such a star, it could be that there's a planet in the intermediate regions between the habitable zone and the planetesimal belt, which is accreting dust before it can reach the habitable zone. And we can also see from the shaded region that there are some systems where the outer planetesimal belt is too faint to detect in the far infrared, but we could still detect its exozodiacal dust. So for example, there were 3 stars in the host survey where they detected exozodiacal dust, but we haven't detected a debris disk. And it could be that they have very faint planetesimal belts and we're detecting dust which is being dragged inwards. And that would be the case if they lied in this shaded region of parameter space. However, not all of this parameter space can be in steady state. So these black lines show the upper limit on the dust mass, which can be in steady state at a given radius from the star for different ages. So belts very close to the star can't be in steady state because they rapidly deplete by collisions. And this just shows how things change for A stars. So overall, we have very similar conclusions to Sun-like stars. So we can then apply our model to the host survey. So here I've shown predictions from our model for the mid-infrared excess as a function of the belt radius from the star. And I've shown 4 different dust masses and 3 different spectral types. Although, as you can see, there is very little dependence on the spectral type. And I've also shown on here the 9 stars from the host survey, which have known planetesimal belts. 2 of these are upper limits because they had non-detections. So the general trend from our model is that as the belt moves further from the star for a given dust mass, we predict a lower mid-infrared excess because the dust is getting colder. However, for the higher dust masses, we predict that we get a plateau around 0.3 to 1%. So we predict that a lot of systems should lie in this region, before the North starts to deplete again for very far out belts. And looking at the host stars, we can also see that a lot of the systems lie in the same region around the plateau. However, there are some exceptions. For example, Eta Cori is exceedingly bright and likely can't be explained by Poynting-Robertson drag. So this has previously been modelled to be due to exocomets being scattered into the habitable zone. And then the two stars with non-detections, as mentioned earlier, we predict that they should have detectable exozodi from PR drag, so it could be that there's intervening planets ejecting dust before it reaches the habitable zone. And then we can also see on here that even very low mass disks can still produce significant levels of exozodiacal dust. So as I mentioned before, the limit for detecting Earth-like planets with direct imaging is around 0.01%. And we can see that even a relatively low mass disk could still produce this level of dust and cause confusion for detecting Earth-like planets. So in conclusion, we have developed an analytical model for size and spatial distributions of dust grains in debris disks, and this can predict how much dust can be dragged into the habitable zone of a star. And we predict that if a star has a detectable planetesimal belt, then detectable levels of exozodiacal dust should be dragged into the habitable zone. And we've also shown that even a very faint belt, which hasn't been detected in the far infrared, could produce enough exozodiacal dust to confuse direct imaging of exo-Earths.